Assalamu alaikum, dear student. This is lecture number 2 of week number 8, and we are continuing the chapter number 7, dimension analysis. So the learning objective of this chapter, still we are discussing the concept of modeling and similitude to develop prediction equation, and also we are discussing the dimensionless variables in data analysis. So let's see the topics we are going to discuss today. We have already covered part of it, the three basic law of similitude. In the previous lecture we have already discussed on it. So just I will go through of it, and then we will go to the next topic, that is common dimensionless group in fluid mechanics. And the last topic of this chapter is practice problems. We will go through many practice problems so that the concept gonna be clear very well. So let's see the let's do a quick review of the three basic law of similarity or similitude. So the first law is geometric similarity. In the geometric similarity, I said that the shape of the object must be same, you can see, and every linear dimension must be reduced with respect to a length ratio. Okay, so here you can see, okay, so all the linear dimension must be reduced with the length ratio, and also all the velocity must be, all the streamline pattern and velocity or the acceleration pattern must be reduced with the acceleration ratio or the velocity ratio. I explained already in the previous slide. And the dynamic similarity, so all the force component, you can see all the force components are reduced with the factor of a force ratio. Okay, you can see, okay, all the factor of the forces, the gravity force, the friction force, and the inertia force are reduced with the same ratio, and the resultant is also reduced with the same ratio. Okay, so the dynamic similarity requires geometric and kinematic similarities. So you cannot attain the dynamic similarity unless the model is geometrically and kinematically similar. So to establish a dynamic similarity, we need to determine the important forces of the prototype flow and make sure that the non-dimensional numbers related to those forces are the same in prototype and models flow. Okay, so to establish a dynamic similarity, we normally take help from the some of the standard non-dimensional numbers, because you see, whenever we solve a real life problem with the standard variables, because all the variables normally do not use in all the natural problems or the every issues, so the variable varies, but more or less it repeats. Okay, so due to this reason, in most of the cases the non-dimensional number repeats. Okay, so the non-dimensional numbers or the dimensionless variables, we specify who repeats frequently in the different cases, we assigned a specific name to them. Okay, some of the pi terms on non-dimensional variables who are commonly repeated in most of the cases are just like rho over v over L into mu. That is basically a Reynolds number. And also another number, that is the Euler numbers, Froude number, Mach number, okay, the Weber number, the Stroll number. But here I will discuss commonly four numbers normally we used in most of the cases. So the most important is the Reynolds number. Okay, So how do we achieve the Reynolds numbers and what it is, and what is the importance of these numbers in the analysis of fluid flow problems? So in fluid mechanics, dimensionless number or dimensionless number are those which are useful to determine the flow characteristics of a fluid. Okay, so these are helpful to determine the flow characteristics of a fluid. Okay, that means the dimensionless similarity or the or the dynamic characteristics. So dividing this inertia force with other forces like viscous force, gravity force, surface tension, elastic force or pressure force gives us the dimensionless number or the pi groups. Okay, so all the dimensionless numbers have a ratio of different forces. Okay, so what about the Reynolds number? So Reynolds number is the ratio of inertia force over the viscous force. So let's verify that, okay, whether this these number or these terms are equivalent to the inertia force or viscous force. So the Reynolds number is the ratio of inertia force to the viscous force. So let's analyze. So here you see this is the Reynolds number, and the Reynolds number, as we see that the basic definition is inertia force over viscous force. So Fi is indicating the inertia force, Fe is the viscous force. So we know that the inertia force is equals to ma. So mass of a fluid is density time volume, okay, multiplied acceleration. What is acceleration? Velocity over time. So this is the density, so we took this T under the volume, so it become volume flow rate. Okay, that is Q. So this will become volume flow rate and the velocity will remain here. So you see, volume over time is equal to the volume flow rate and V is the velocity. So the inertia force will become density times the volume flow rate into velocity. So further, the volume flow rate, we know that it is equal to area time velocity. So finally it become density time area into velocity square. Now the viscous force. So viscous force, we know that according to the second law, according to the Newton law of viscosity that we derived in the first in the topic of viscosity. So that is shear stress is equal to mu times shear stress is equal to mu times velocity gradient. Okay, velocity gradient is a change in velocity with respect to change in depth or change in height multiplied by the area. Okay, so this will give you basically the, so if we multiplied the shear stress, okay, multiplied by the area, okay, you will get the viscous force. Okay, so here, so what is tau? Tau is basically the shear stress. Okay, the shear stress was equal to viscosity times velocity gradient V over L. Okay, or that is multiplied by the area. Area is here. Okay, so this is mu V over L. So this is the viscous force. So now put the value of these two forces with respect to the fluid that you have calculated. If you put them here, so what will happen? The V square will cancel with the V and A will cancel with the A. So finally it will reduce to V L over mu. Okay, so it will reduce to like this, rho V L into mu. So let's see, you see this same component here, rho VL over mu. So this is the Reynolds number. So it proves that the Reynolds number is the ratio of the inertia force over the viscous force. And we can also write down VL over nu. This is the dynamic viscosity, and this is the, and this nu is basically the kinematic viscosity. So we can write down the Reynolds number in the form of dynamic viscosity. Okay, this is and also in the form of kinematic viscosity. So another important number is the Froude number. So another important number is the Froude number. So what is the Froude number? Froude number is the square root of the ratio of the inertia force to the gravitational force. Okay, it is the ratio of, it is the square root of the ratio of the inertia force to the gravitational force. So let's see the Froude number. It is the under root of inertia force over the gravitational force. So inertia force just now we have calculated, that is rho a v square, and the gravitational force we know that mass into gravitational acceleration. So we simplify the mass in the form of fluid. So the density of the fluid the rho and the volume. Okay, the mass is equals to density time volume, and volume is equals to what? Volume is basically a 3 dimensions, area into length multiplied by the gravitational acceleration. So the gravitational force will be equal to density times area into length into gravity. So put these values in this equation. So this is rho a v square is the inertia force, and rho a lg is equals to the gravitational force. So here a and a will be constant, so v square over lg, and v square is equals to, so v is not v square, is going to be v only. Okay, so please make it correct, it's only v. So v over lg. So let's see the Froude number. You can see here the Froude number is v over under root gl, same that we have derived. This is not v square, this is v. So v over under root lg. So let's see the another important number, that is basically a Euler number. Euler number is the ratio of pressure force to the inertia force. Okay, it is the pressure force to the inertia force. So let's see here. So in this way you can derive the Euler numbers and as well as the Weber number. Okay, so the Weber number is the ratio of inertia force over the force of surface tension over under root. So inertia force over surface tension force. So inertia force we know equal to this, and the surface tension force is equal to, we know that the surface tension is equal, the force of surface tension is equals to sigma into L. Okay. So the surface tension is equal to force per unit length. Okay, so when you put the values, what will happen? The length and length is going to be cancelled. Okay, v square is going to be inside. So finally v over sigma under root sigma over rho. So here is the derivation of some of the numbers to verify that these numbers are basically the combination of different type of forces. So let's see where those numbers normally we use. These numbers we cannot use in all the problems. So these numbers are basically used in the specific problems. So here you can see the important question is how to decide on the important force type for a given problem. How would we know that? Okay, which forces are involved in this problem? So which combination we should use? In other words, equality of which non-dimensional numbers should be sought. So here we can see some of the application of these numbers. So Reynolds number, where we can use the Reynolds number. Reynolds number similarity is important for almost all the flows. Wherever the pipe is, wherever the fluid is flowing, in the open channel or in the closed channel, in the pipe or in the open channel or trench. Okay, so in those areas the Reynolds number must be used. Froude number similarity is important for flows with free surfaces. Wherever there is a free surface, such as ship resistance, open channel flows, and for flows driven by the action of gravity. So wherever is the gravity force is involved, okay, so just like a free discharge flow, okay, the open channel flow, okay, so in these areas, and where in the ship, because when the ship is sailing, so it strikes a huge amount of water in the form of big waves, okay, because those water has a weight and that try to stop the ship to sail, okay. So in that case we use a Froude number, because the Froude number is the ratio of inertia force as well as the gravitational force. In the same way, the Euler numbers, similarity is important mostly for turbo machinery's flow, okay. So this number is basically helpful in the case of a turbo machinery flows with considerable pressure changes. So wherever there is the involvement of the inertia force and the pressure force, okay, the Euler numbers is useful, for which cavitation may be a concern. So wherever there is a case of a pressure difference, okay, so this number is very helpful, okay. So the Weber number, similarity is important for problems involving interfaces, okay, wherever we have a different fluid or different two surfaces where the surface tension is important, okay. So with density change and lightweight objects, okay. So wherever the surfaces are changing, wherever the interfaces are involved, okay, the Weber number is involved, because the Weber number is the ratio of the inertia force over the surface tension force, and so on. After deciding, okay, so here you can see, after deciding on the important parameter of the problem, which is not always an easy task, Buckingham pi theorem will also end up with these numbers, okay, because once you find out these numbers by using the Buckingham pi theorem, okay, then you can solve the problem very easily. So here you can see, to establish dynamic similarity, we need to determine the important forces for the prototype flow and make sure that the non-dimensional numbers related to those forces are the same in prototype and the model flow. Here is one example we can see that how to use a dimensionless numbers for a particular problem. So in the example you can see it says the aerodynamic drag of a new car is to be predicted. So we have to predicted a drag force over a car at a speed of 100 km per hour at an air temperature of 25 degrees centigrade. So we want to run our prototype or real life object at the in the temperature of 25 degrees centigrade of air, and air has a velocity of 100 km per hour. So the engineers built a 1/50 scale of the car to test in a wind tunnel. It is winter time and the air in the tunnel is 5 degrees centigrade. Determine how fast the engineers should run the wind tunnel in order to achieve similarity between the model and the prototype. How each Newton of drag force measured on the model be transferred to the prototype. So we have to find out the force ratio, okay. So here normally you see in the wind tunnel we take the air from the surrounding, and since it is winter, so we do not have a air of a 5 degrees centigrade, so we have a air of a we do not have a air of 25 degrees centigrade, we have a air in the surrounding 5 degrees centigrade. So how we can compensate this difference of temperature in the force ratio, okay. So since we are talking about the drag and all the variables we used in the in the drag force. Okay, so in the case of the drag force, we know the important important dimensionless variable is the Reynolds number. Okay, so the Reynolds number use all the variables. Okay, so to analyze the dynamic similarity, we take the Reynolds number. Okay, so the Reynolds number for the prototype and the Reynolds number for the model. Okay, so we can separate the ratio because the length ratio is given 1:5, so we can change it to length ratio, and accordingly we can find out the if length ratio is known, we can determine the velocity ratio. If the velocity ratio is known, you can easily determine the dynamic ratio. Okay, that we have discussed previously. So let's solve some of the problems so that the concept to clear the concept. Okay, so here the time t it takes to pour a certain volume of liquid from a cylindrical container depends on several factors, including the viscosity of the liquid. Okay, as assume that for very viscous liquids, the time it takes to pour out 2/3 of the initial volume depends on the initial liquid depth L and the cylindrical diameter d, the liquid viscosity mu, and the liquid specific weight gamma. Okay, so here the pouring out time, okay, the pouring out time is depending on certain variable, that is length of the container. The length of the container or cylinder is L and diameter of the cylinder is d, liquid viscosity mu, and the liquid specific weight gamma. Okay, so the data shown in the following table were obtained in the laboratory. For these tests, L is equals to 45 and D is equals to 67 mm and gamma is equals to 9.60 Newton per meter cube. Okay, so the data is taken, okay, with these initial values given. Okay, so yeah, the data is given here. Okay, it takes time, the viscosity is this much and time is equals to 15 seconds, 23 seconds to pour out 2/3 of the liquid. So this is the viscosity of different liquids, and the viscosity, the liquid took 15 minutes to pour out 2/3 of its initial volume. So what we have to do, we have to perform, and what is the size of the container? The size of the container is the length of the cylinder is 45 mm. So perform a dimensional analysis, and based on the data given below, determine if variables used for this problem appear to be correct. So first of all, we have to verify that we have to determine the dimension, we have to do the dimension analysis, and second, we have to confirm that the variable we have considered to solve this problem is correct. Okay, and explain how you arrive at your conclusion and how we can say that the variables are correct. Okay, and how we arrive to this conclusion, the variables we have selected to solve these problems are correct. If possible, in the B, so if possible, determine an equation relating the pouring time and viscosity for the cylinder and liquids used in these tests. So also we have to develop a relationship between the pouring time and the viscosity, okay, for the cylinder and liquids used in this test. So this is the cylinder diameter, the length, and the specific weight is used. Okay, if it is not possible, indicate what additional information is needed. So First of all, what we have to do, we have to do the dimension analysis, and to do the dimension analysis we use a Buckingham Pi theorem. So we know the step of Buckingham Pi theorem. First of all, we write down the total dependent and independent variable. So the time is depending, okay, the pouring out time is depending on the following variables: the length, the diameter, the viscosity, and the specific weight, or the weight density. Okay, so the total number of variables are 5. So we have write down the all the variables in the form of dimensions. Okay, so the total number of variables are 5 and the total number of reference dimensions are 3, so equal to 2. So total number of pi terms we have 2 pi terms. So we are required 2 pi terms to explain the phenomena. So here you can see 2 pi terms. So we know the procedure. We took the procedure of repeating variables. We consider the repeating variables, okay, and based on that we solve the problem. The first pi term we made it, pi 1 is equals to T gamma D, and we can recheck if this pi term is correct, is the dimensionless number. So we cross check that. So we got m naught, l naught, t naught. So that means this pi term is correct. The second pi term is we got L over D. Okay, so you have to solve it the way we used to solve. So you will get this another pi term, that is L over D, and under 100% it is a dimensionless number. Okay, so the time, this is a dependent pi term and this is the independent pi term. So this pi 1 is a function of pi 2. So that means this term T gamma D over mu is equals is the function of L over D. So this is the equation 1. We got it by using the pi theorem. Okay, so now let's analyze. So let's analyze the variables we have used to indicate the phenomena are correct. So for the data given, okay, what is the data given? Length over D, L over D, 45 or 67, this is 0.672. So it is a constant, you see. So L over D is a constant because we do not have any variable that is varying. Okay, so it is a constant. Thus from equation 1, with L over D a constant, it follows this term also must be constant, because you see, so L over D is a constant, so this term is also equal to constant. So when we multiply all these factors, the value must be same. Okay, so regardless whatever is the density, whatever is the specific weight, whatever is the time, but the end result must be constant because L over D is a constant. Okay, so here what we did, so we T gamma over D. So T is given for every fluid and the viscosity is given for the every fluid. Okay, but the basic dimension of the cylinder and the specific weight is constant. So we put the value of all 4 variables and we calculated the values. Okay, so we put the time here, you can see we taken mu is equals to 11 Newton second per meter square. So you have to make sure that all the units are in the same system. Okay, if it is SI system or the FPS system or CGS system. Okay, so is all of them in an SI system. So here you see I used 11 for the viscosity, the value is 11 and time is 15. I got this value 877. For second I put this value, I put this value, and final. So in the second part we have to drive a relationship between the time and the others. So since pi 1, so the average value of pi 1 is 874, so here you can see the values are almost constant. Okay, so that means the value we have selected is true. So to develop a relationship we have took average value, and this is the relationship we have developed. Okay, so T is equals to 1.36 into mu with the given values, okay, for a particular case. So with T is in second, where mu is in units of Newton second per meter square, note that this restricted equation is only valid for L over D, okay, which is given, okay, for 0.672, and D is equals to 67 mm and gamma is equals to 9.60 kilonewton per meter cube, with 2/3 of the initial volume being poured, okay. So this equation is valid only for this case, okay. So this is end of the problem, and rest of the and some of the remaining problems we will discuss in the next lecture.